Hello everybody, good morning, good afternoon, good evening. So everything is applicable here. So I'm Najmul Haque and I'll be talking about Gribov quantization and its effect on deconfined nuclear matter. So I'm from NISA, this National Institute of Science Education Research. I'm from the physics department. So yeah, so these are the brief outline of my talk. So in first few slides, I will just briefly tell something about the standard textbook material. Then I will move to some result about this Gribov quantization. Then in the end, I will discuss something that we have recently done. Okay, so at first I will discuss this Faddeev-Popov ghost, the concept of ghost, then what is the problem with that, and Gribov ambiguity. And this Gribov thing that was introduced to define this confinement. So we have some confinement scenario. So is this applicable to the deconfined phase? I'll discuss a little bit about that. Then using this Gribov summation, I'll discuss the Gluon Thermodynamics. Then I'll move our recent calculation, that is covariant kinetic theory with this Gribov summation. Then I will also show some plots for the transpose coefficient. Then I'll conclude. Okay, so this Faddeev-Popov ghost, what is this thing? So everybody, I think, know, but I will discuss a little bit. So I'll start from very basic Yang-Mills action. So let's say we have this mu field tensor with color indices A, and considering this only the Yang-Mills portion without this quark part, we can write down the generative functional for this Yang-Mills action, and that will be indicated of these fields, the gluonic field A. And if you have some source term, that is mu A, that should be also added to the action. That will be e to the power minus s in Syn plus the source term. And this functional is not well defined. Okay, so we have a problem. So what is the problem that we'll discuss now? So if you take the quadratic part of this action, so we have this mu, so we have various order of term. So if you just concentrate on the quadratic term, so that you can write down in this way, this functional, generative functional for the quadratic term, and you will get a determinant of A into this mu term. Okay, so mu, what is this mu? So this is basically the 2-point function in the coordinate system. So this is basically the Gluon propagator. So you can get the momentum, this Fourier transformation of this quantity, and you can get momentum dependence propagator also. So to calculate the propagators, so you need this inverse of this determinant of A. Okay. So to calculate the inverse, you have a problem. We cannot take the inverse of this mu. This is not invertible. Okay, so we have a problem. So to get rid of this problem, we can choose some gauge. So we know the concept of gauge from the electromagnetism. So if we add some extra term to the potential, electric and magnetic field remain same. So we'll use the same concept. We'll use some, we'll choose some gauge, and we'll add some term in the Lagrangian, and we'll see what will happen. So there are many choices for the gauge. One of the choices is covariant gauge, and the covariant gauge is the extra gauge fixing term is 1 by minus 1 by 2 xi. Xi is gauge parameter into fourth derivative of the field. Okay, and that's square. Okay, this is the choice in covariant gauge. Okay, so if we use this covariant gauge, if we add this gauge fixing term to the Yang-Mills action, you can now invert the propagator. You can get the Gluon propagator in this way. Okay, the first equation, sorry, here in this way. So delta AV is the color factor. So if you consider the Gluon, so delta function tells you if the initial color is A, final color should be A, and we have this momentum of the full momentum of the Gluon, that is capital K, and this parameter xi that becomes 1 minus xi, and we have other quantity also. Okay, so now we got the propagator, the Gluon propagator. We can invert this, and we can write down the Gluon propagator, but this is not the end of the story. So we have some other problem. So till now we have discussed this non-abelian theory, the gluonic case. So it is easy to understand this case for the electromagnetic QED case or abelian theory. And for that, we will just simply choose the ion gauge group, that is the abelian gauge group. And if you just consider, so you can also show this for the non-abelian case. So I just choose to show for the abelian case. So if you consider this transformation of this fields mu, that transform as mu theta, sorry about this point, mu theta plus 1 by E electric charge into derivative, local derivative of the theta. Okay, del mu. So if you can choose this type of gauge transformation, you can go back to the generating functional, and because of this extra gauge choice, the generating functional should have a term, and that is something like this. So you have to, so that is a product of all the x value, and there will be the theta term, and this term you are actually taking products for all possible possible configuration. That is why this term is in general infinite. So we have a problem. You cannot calculate this generative function. If you can calculate the generative function, you cannot proceed further. Okay, so we should find a way so that these extra infinite factors can be factored out, and if you can factor out outside the integral, it is possible to absorb with the renormalization constant, and we can define that constant as renormalized constant. So if there is a way to extract that factor outside the integral, and this was done by Ludwig Faddeev and Victor Popov in 1967. So they proposed a way, that the way was to multiply the both sides with identity. So left hand side we have a 1, and right hand side you have integral over the field A. So if you multiply the both sides, and it is possible to extract that factor out. And if you do all the calculation, in the end of the day, it is same as to add another term in the Lagrangian, and this term we call this ghost term, and corresponding action is S ghost. Okay, so sorry. Okay, so we got this Yang-Mills action, that is the normal Yang-Mills action. We have a gauge fixing term that we have introduced earlier. That could be covariant gauge, that could be any other gauge also. And apart from that, we need a ghost term to integrate that infinite term, take the outside, and you can absorb that with the renormalization constant. Okay, so notice that by fixing these gates, I mean both gauge fixing and ghost term, we have introduced an extra particles, that is C and C bar in this equation, C and C bar. So these particles are called ghost, and those particles are scalar and anti-commutative. And so that is why you can say this wireless the spin statistics. What do you mean by wireless spin statistics? So that means if you consider the fermionic field, that is well known, and for the fermionic fields, they actually anti-commute, and that is not scalar, that is fermion. So these fields is anti-commuting but scalar, and that's why they actually vary the spin statistics. And for the theory to be physically acceptable, because we don't know, we don't find any ghost in nature. So to be physically acceptable, this proposal by Faddeev and Popov, the ghost particles should be virtual particles. That means they only should appear in the internal line in the Feynman diagram. So they cannot appear as a leg in the Feynman diagram. They only appear in the loop. Okay, so in the end of the day, we will integrate about this loop and we will get some contribution, but there is no physical spectrum for this ghost. Okay, so till now everything was fine. We have fixed the gates, we got new virtual particle, that is ghost, and everything was working fine. So now that is again not end of the story. We have another problem in this case that is actually known as Gribov ambiguity, and we will discuss about this. Okay, so in 1978, Gribov first actually demonstrated that this gauge condition, the proposed by the Faddeev and Popov, that is not ideal. We have some problem in that also. So what is that problem? The problem was that Gribov considered the question of given a certain physical configuration, how many different gauge copies you can consider? How many different gauge copies of the configuration over this particular gauge condition? So if you consider this covariant gauge, how many possible gauge copies are there? Okay. So and there could be various many gauge copies for a particular gauge choice. And so if you consider, just for the example, if you consider two gauge field, that is A mu A is the color indices and mu is the noise indices. So if you consider this A mu A and a gauge field, that is A mu A prime, and assume they both satisfy the lambda gauge condition. So we are just considering the particular gauge choice, that is lambda gauge. So we have discussed on the covariant gauge. In lambda gauge is del dot A, that is the 3 derivative actually 0. Okay, so if you so del dot is 0 in lambda gauge. Okay, so they both obey lambda gauge condition. So if this prime fields is a gauge copy of the non-prime fields, so they should actually transfer like this equation. So A prime should be A plus covariant derivative and some quantity, that is omega into B. So what is omega? That is actually gauge freedom that you are adding, and that will satisfy the same equation of motion. Okay, so it did both fields obey the lambda gauge condition, so del dot A is 0. So this quantity del mu into this quantity, that will be 0. Okay, so the Faddeev-Popov operator, so I didn't say anything about the operator, so that operator actually appears when you introduce this S ghost in the action. So this Faddeev-Popov operator has at least on 0 mode. So from this expression, you can actually conclude that on 0 mode. And if the gauge field is very, very small, that omega is very, very small, the operator will not have any 0 mode. Okay, so you are making omega tending to 0. Okay, so then there is no problem, and this quantity itself is 0, left hand side. So there is no problem, and operator will not give a 0 mode. So that sets of gauge that has first 0 mode is called the Gribov horizon. So starting from the origin, if you increase the value of omega, the various gauge set of various gauge. If you increase it, so at some horizon, you will get the first 0 mode of the Faddeev-Popov operator. Okay, so this first 0 mode is called Gribov horizon. Okay, so the set of all gauge group inside this first Gribov horizon, and that has no 0 modes, is called the first Gribov region. Okay, so we got some first Gribov region, we got some first Gribov horizon, and if you consider all the gauge fields that have gauge copies, and those fields will be overcounted in the part integral, and either in order to overcome this problem, just consider the region of first Gribov horizon. Okay, so consider the region starting from the origin inside the first Gribov horizon. Don't go outside the first Gribov horizon, and choose only the gauge copy that is inside the Gribov region. Okay, so in this way we can overcome the overcounting that is appearing because of the various gauge copies of a particular gauge condition. Okay, so in order to do so, the Gribov considered the ghost propagator, and that is nothing but the expectation vacuum expectation value of the inverse Faddeev-Popov operator. And if this operator is always positive and definite, the ghost propagator cannot have poles. So that means when you are considering the ghost propagator, inside the first Gribov region, there is no poles in the Gribov propagator, and that is called no pole condition. So somehow you are restricting the region in which you are choosing the gauge copies. Okay, so this is some way out to actually not to consider all the gauge configuration, so that by restricting yourself to the Gribov region. But in usual perturbation theory, what do? We do the propagator has poles, that we know, and which means we left the first region, and we overcome some actually configuration. Okay, so how to do this? How to restrict ourselves to the first Gribov region? So not to cross that region. So to do this, so we actually, we understand that we have to restrict the in some region. So that can be done in this way. So we can write down now the partition function only for the Yang-Mills fields. There is no quark. We are just considering Yang-Mills fields. And the partition function you can write down in this way: del A term, del A into del dot A, that is the gauge condition, and we have determinant term. But if you want to restrict yourself within the first Gribov region, that is we call this omega, you have to multiply with a term, with a function that will say b omega. So without this b omega, that is the usual partition function, but when you are introducing this b omega, you are restricting yourself to the Gribov region. Okay, so if you do so, we need to find the form of this this function b omega. Omega means this Gribov region, and that you can actually do with this step function, theta actually step function. So if you take this 1 minus sigma 0, that quantity is positive. So that is why you can actually that's how we can actually restrict yourself to the first Gribov region, and that quantity sigma is actually the inverse of the 1 minus sigma, actually the inverse of the Gauss-Desing function. So you can write down the free Gauss propagator, and you can multiply the function that is ZG, and that's called the Gauss-Desing function, and 1 minus sigma b is nothing but the inverse of the Gauss-Desing function. So that you can write down in terms of 1 minus sigma in the right hand side. Okay. So we have introduced a integral variable, that is beta, to get this right hand side. So this integral variable beta is identified at the Gribov mass or Gribov parameter. So there is no Gribov parameter, and we'll identify. So that can be identified. That was done in some later years. So that was done, and if you just redefine beta with some redefinition, you can create the Gribov mass parameter gamma g. Okay, so we got some, at the end of the day, we got some mass parameter, and we got the modified Gauss propagator also. So with this gamma g, this redefined Gribov mass parameter, it is possible to rewrite our well-known Gluon propagator that we have already seen earlier. Okay, so this is the well-known Gluon propagator, and in that equation we have introduced another factor, that is gamma g. So if you take gamma g tending to 0, what will happen? The right hand side, this term, this last term, that will be 1 by p square, and that is nothing but the normal perturbative Gluon propagator. So in presence of this Gribov term, when you are constraining yourself in the first Gribov region, you got this contribution, extra contribution. And as you can see, if you take p tending to 0, we have some infrared suppression because of this gamma g term. Okay, and that actually tells you the confinement of gluons in this scenario. Okay, so starting from the Faddeev-Popov Ghost, and by coming to the Gribov ambiguity, we got some expression of the Gluon propagator considering the Gribov mass parameter. Okay, so we got the propagator. Now the question is whether this Gribov confinement, we are saying confinement because it p tending to 0, this term is finite actually, that tells you some signaling about the Gluon confinement, and whether this can be applicable in the deconfined phase. So deconfined nuclear matter, in which the confinement is, so we have this confinement is gone, and as I said, Gribov is some type of signaling of confinement, whether that is applicable to the deconfined phase or not. Okay, so for this discussion, whether this Gribov confinement scenario is applicable in deconfined phase or not, I have taken this description, this discussion from this John Zinger paper, PhD 76, 2007 paper. So in that paper, he described in details the applicability of Gribov confinement in the confined phase also. So it is well known that if you consider the color Coulomb potential between two quarks, so quarks and anti-quarks, the Coulomb potential actually in linear, that is actually d Coulomb into the distance between the quark and anti-quark. And if you take d Coulomb, so and this d Coulomb is not the physical string tensor between the quark and anti-quark, that is actually some proportionality factor, that is 3 sigma, and that is the potential between the quark and anti-quark pair. Okay, so numerically it was found that if you go beyond Tc, that is when the temperature of the system is greater than Tc, phase transition temperature, this linear behavior is still there. Okay, so that is found in lattice calculation. And so if this linear behavior is there, what about the sigma Coulomb? What is the nature of the sigma Coulomb, the effective skinning constant in this case? What is the effective skinning constant in case of deconfined matter when T greater than Tc? Okay, so this effective sigma Coulomb to the power half, that was found actually, that is proportional to the G squared T at high temperature. So that means this Coulomb skinning actually, the scaling as magnetic scale of the system. Okay, so T is the hard scale, GT is the electric scale, and G scale is the magnetic scale. So that working as a magnetic scale of the system at very high temperature. Okay, so from this conclusion of this paper, and also from lattice studies, one can say that we can also use Gribov mass parameter. We can introduce the Gribov mass parameter to the deconfined phase of the matter. Okay, so this is the motivation to actually include this one, and there are a lot of works that has been done considering the finite value of the gamma G, the Gribov mass parameter. So I will discuss some works in this direction. So at first I will discuss the Gluon Thermodynamics. Okay, so consider a system that is consists of pure gluons, and if you consider we have this Gribov confinement, Gribov summation is present. We have this gamma G non-zero. Then what will be the thermodynamic properties of the system? Okay, so that was done. So in our knowledge, this was passed on to calculate this thermodynamics in 2005 by the parallel paper by Daniel Janzinger. So what he did, so we have this gamma G, and we know the form of this gamma G. So he fixed this gamma G, the unknown parameter, with the lattice stress anomaly at the high temperature. So you can see from the right hand part of the figure, the trace anomaly, the red dot is the Gribov, the contribution that is coming from the Gribov plasma, and that is actually matching with the high temperature region. And he fitted the high temperature trace anomaly with the lattice. He got some expression of gamma G, and with this gamma G, he calculated the other thermodynamical quantities. So in the left part of the figure, it is energy density, entropy density, and pressure with respect to T⁴. Okay, so this is one of the way that was introduced by Janzinger to calculate the gamma G. Okay, so so that was some work in that direction. So in later, so there are lots of work also in this direction. So in 2013, Nansu and Kenji Fukushima, they calculated this gamma G quantity in some other way, not following the procedure that was adopted by Janzinger. So what they have done, they have taken the ghost propagator, they have applied the variational principle, and they got some gap equation. So that gap equation, if you solve this gap equation, and this G square is actually running coupling constant. So if you get this gap equation, and if you can solve this gap equation, and you will get the expression of gamma G here. Okay, so by solving this gap equation, they got the expression, and get this below this expression. And it is not possible to solve this gamma G analytically. So I will discuss some quantities here. So we got this capital lambda. What is capital lambda? So capital lambda was introduced to as a renormalization scale. This was done in this dimensional regression technique. And for that, we need to modify the three-dimensional integration. And for there, this lambda was introduced, and we have a scale in the theory. Okay, so E plus and E minus, and that is the energy of the gluon that is coming from the Gribov propagator, Gribov-gluon propagator. Okay, and NB is the Bose-Einstein distribution function, and you got some equation. You can calculate this gamma g with some choice of lambda, and that will be some numerical solution. But it is possible to calculate gamma g in asymptotic limit, say at t tending to 0, at t tending to infinite, and they have done it. So with the numerical solution of gamma g, they have calculated the trace anomaly and also the pressure, scaled pressure, and the trace anomaly. So I'll discuss the various curves. So red curve here is the solution that they got solving this gap equation and putting into the thermodynamic quantities. And we have another band that is this band. It's not getting selected. So we have another band that is gray band, and this gray band is coming. Actually, this is due to the 3-loop HTL for the pure gluon case. So this is without considering the quark contribution, only the gluon contribution. And this start points are from the lattice data, and that is this lattice data from Upetal Budapest group 2012, I think. Yeah. And in the right-hand side of the plot, trace anomaly has been plotted with this lattice data, also three-loop HTL band. So this band is appearing due to the choice of this renormalization scale lambda that is appearing in the gap equation for the solution of lambda g. Okay, so we have discussed about two types of procedure to extract lambda g. So one was gap equation, and is fitting lattice data at high temperature. Okay, so I'll discuss some other calculation in this direction. So another calculation was this Gribov term as a magnetic scale summation in HTL. Okay, so I'll tell you briefly what is a hard-thermal loop, that is HTL. So HTL is hard-thermal loop in which we actually consider we resum the soft contribution, that is order of GT in the theory, and to do this we actually calculate on-loop effective self energy, on-loop effective propagator, everything. So this calculation was done by Najmul and Conrad. I think Conrad is also here present, I don't know. So that was done in 2015. So what they have done in this calculation, they have considered both the electric scale and magnetic scale summation in the calculation. So in normal HTL, we only consider the electric scale summation, and if you consider the magnetic scale summation also, so in normal HTL, you got two bands in the left part of the plot. You got two bands, that is omega plus and is omega minus. Omega plus is something like quasi-particle holes. The quark gets some thermal mass in the medium, and omega minus is some plasmino modes that actually appears due to the medium effect. And if you add this magnetic scale summation in the theory, you get another new branch that is called omega z. In the right hand side, you can see we have a blue band, extra blue branch, and that is purely coming due to the this asymptotic form of the Gribov diameter at the high temperature. Okay. So that was in 2015. In 2016, we have used this dispersion relation to calculate some other quantities of the deconfined medium, and we have used this magnetic scale summation for the quark propagator to calculate the quark number susceptibility and also the dielectron rate from the deconfined medium. So that was done with collaboration with Oito, Munshi, and Mike. In 2016, and we got some result, and our conclusion was the magnetic scale resummation actually is making our result was not actually improving anything. So our conclusion after this paper was the resummation of magnetic scales fails to improve the existing result at on-loop level. So I'll tell you what was the thing that actually appears in that calculation that actually making the result worse, not the improvement. So, you know, we have a Landau damping appears in the A-scale case, Hadhamar loop case. So that happens when the energy K0 is less than K. Okay, so that tells you propagator has a imaginary part, and that gives you Landau damping. So this Landau damping part has actually contributed to the quark number susceptibility, also to the dielectron rate. But in the Gribov scenario, we find that this K0 that is actually getting modified, this K0 is energy actually that is getting modified because of the Gribov term, and that is always greater than K. You should not get any Landau damping scenario, at least with this magnetic and electric scale information in the scale scenario. So that is why we actually lost a good amount of contribution because of the Landau damping in the quark number susceptibility, also in the damping layer, and that is why the result fails to improve the existing result at on-loop level. Okay, so after this literature survey, literature discussion, I will move to a recent work that I have done with Omois Joyshal. So in this calculation, what we have done, we have built the covariant kinetic theory with this Gribov desummation. Okay. So to discuss this, we need to write down the equilibrium energy momentum tensor that you can write down. So zero here means equilibrium quantity. Okay, so we can write down the equilibrium energy momentum tensor, and we have some integral measure, and we have some Gribov dispersion relation present in this case. Okay, so gamma g is the same Gribov parameter. So if you don't take Gribov parameter, this is simply p square, that means p0 square minus p square, and because of the gamma g, the dispersion relation gets changed. So we have introduced this quantity, and we have introduced this one covariantly. And to get the thermodynamic consistency, we need another term, that is B0, that is something like bag constant, and that bag constant can be calculated from the thermodynamic consistency. Okay. Okay, so for this equilibrium energy momentum tensor, we can calculate the equilibrium pressure, energy density as P0 and epsilon 0, and P0 can be calculated by minus 1/3 into projection of T mu nu along delta mu nu, and that basically gives you Pg minus P0. So Pg is basically coming from the first term, this whole first term, and that actually comes from the quasi-particle poles of the Gribov propagator. Okay, and B0 is coming from this second term. So similarly, we got this equilibrium energy density as epsilon g plus B0. Okay, and this P0 and epsilon g, what are those quantities? Those are the pressure energy density that actually arising from the thermal Gribov thermal distribution of the gluons. Okay, so and as I have said earlier, so we have this Gribov propagator. In the denominator, we have Gribov 4 plus gamma g to the power 4. So that means we have quasi-particle poles at P0 equal to E plus minus, that is P square plus minus I gamma g square. So we got imaginary energy and imaginary poles, and that energy is P square plus minus I gamma g square. So with this imaginary poles, we can calculate this Pg, the contribution to the pressure due to these quasi-particle poles, and that turns out to be plus, because we have this plus pole and we have minus pole. If we add those two poles, that will give you the real pressure energy, and that should be okay. So we can go back to the T mu nu 0, and we can get the thermodynamic consistency. The relation between pressure, energy, and entropy. So from this thermodynamic consistency relation, we can get the derivative of B0 is related with this gamma g in this form. Okay, so we have two quantities that we have to fix. One is B0, one is gamma g. So we are not taking gamma g from previous literature, we are fixing that from this calculation. So we have to fix two quantities. So this Gribov parameter gamma g can be fixed matching the lattice equation of state. So what is the difference from this one to the calculation that was done by John-Zinger? So John-Zinger fitted the result for the high temperature part. So what we have done here, we have fitted for the whole range of the temperature. Okay, so Gribov parameter gamma z is fixed by matching the lattice equation state. Okay, and back-like function, this B0 is obtained from this thermodynamic consistency relation. Okay, so we got some way to calculate these two unknown quantities, that is gamma z and B0. And this is the fitting of lattice result from this orbital Budapest group in 2012. And so we got this fit formula. See, this fit formula was not present in that paper, this JF paper. So what we have done, we have taken the same formula that was used to fit for the quark-gluon thermodynamics. So we use that same fit formula for the gluonic case, and surprisingly we got the good fit, which new sets of parameters. So by fitting the lattice data, this red dot, we got the values of these various constant H, F, G, and blue line is our fitted result. And if we fit the pressure, we can calculate the gamma Z, and we can also calculate B0 from the thermodynamic consistency equation. Okay, so we got thermodynamics for the Gribov plasma fitting the value of gamma Z from the lattice. Okay, so that was the equilibrium case. So to study non-equilibrium case, you have to study the transport coefficient. You have to go to the non-equilibrium case, and we can write down the T mu nu with non-equilibrium distribution function F and non-equilibrium back pressure B. Okay, so this non-equilibrium back pressure, we can write down equilibrium back pressure plus some quantity delta B, and this T mu nu that should also satisfy the energy momentum conservation, del mu T mu nu equal to 0. And from this T mu nu expression, if you take the conservation of energy momentum density, we should get del mu V equal to del mu gamma Z into this quantity. Okay, so we got this from the energy momentum conservation equation. And so if we want to match this equation to the equilibrium case, okay, so this so we have to identify this bracketed quantity, this particular quantity in non-equilibrium case with the Boltzmann equation. Okay, so extend this thermodynamic consistency to the non-equilibrium case, the bracketed quantity actually becomes related with the Boltzmann equation, and that we have to introduce some kernel in the right hand side, the CF, and this left hand side is nothing but the bracketed quantity in the previous equation. Okay, so we got the Boltzmann equation for the non-equilibrium case. We can use some approximation to get the kernel. We can use the relaxation time approximation, and this kernel will be related to this tower relaxation time, and that we can write down with this delta F. So distribution function minus distribution function at the equilibrium. So we got this delta F. So the out of equilibrium case that we are discussing, the density can be written as this F into capital F0 plus delta F. So we are introducing another notation, this capital F0. So what is capital F0? What is the difference between capital F0 and small f0? So capital F0 has the form of local equilibrium distribution, but with non-equilibrium Gribov parameter. But if you consider a small f0, that is with equilibrium Gribov parameter. So that is the difference between this capital F0 and small f0. And we can get the deviation from equilibrium, the defined quantity. So we have three quantity that actually we have to calculate in non-equilibrium case. One is this gamma z square, the Gribov mass parameter, the distribution function delta F, and the back pressure delta B. Okay, so we got some scalar function. We have denoted this INQ and JNQ that can be calculated from this equilibrium distribution function F0 and F01 plus F0. Okay, so yeah. So to calculate the transport coefficient, we need to the distributive quantities we can write down in terms of delta F and the shared tensor that can be written as P mu, P alpha, P beta into delta F when this with the symmetric testless projector orthogonal to U mu, and you can also write down the bulk pressure as capital pi. Okay, so So this is in this expression we have total delta F in the first equation. So we have to take some approximation to calculate this delta F. So we can take this first order correction, and we can write down this capital delta F1, and from the capital delta F1 from the Boltzmann equation, and we can get this expression. So again, we will use the thermodynamic identities. We will take the projection to the energy momentum conservation equation. We will take two type of projection, and so we will get two equations. One is time derivative of the temperature, and is special derivative of this quantity temperature T. Okay, so if you do this, you can put this T dot and del mu T back to the previous equation, delta F1, and we can write down this delta F1 in this way. Okay, so here we got a tensor delta sigma mu nu that we will denote later. Okay, so we got capital delta F. Okay, but to calculate the transport coefficient, we need small delta F. So we know the relation. We can put back this capital delta F to that equation that we got earlier. We can invert that for the delta F1, small delta F1, and we got some expression for the delta F1. Okay, so if you get delta F1 in the first order approximation, we can easily calculate the shear and stress tensor. So, and you can get the well-known Navier-Stokes equation, that is shear this pi mu nu, that will be 2 eta into sigma mu nu, and you will get some expression of the coefficient of shear viscosity in terms of this K, that is the Bessel's function of the second kind, fifth order, third order, and first order, and we have some other function that is similar to the Bessel's function, but yeah, that is something different, so that is special function. And this is the contribution for the energy with the plus I, and we have also contribution from the minus I. Okay. Similarly, we can calculate the bulk viscosity coefficient. I am out of time, I think. So yeah, bulk viscosity coefficient, and you can write down. So you see, so we have a term in the bulk viscosity coefficient that is proportional to the gamma g to the power 4, and we know gamma g to the power 4. So if you take gamma g to the power 4, that is actually this bulk viscous coefficient that actually vanishes, and that should be. Okay, so ultimately we can plot that for the gamma g that we got by fitting the lattice data, and we got a peak of the bulk viscous coefficient at around t equal to Tc, and also we got eta, that is actually increasing function of T by Tc. Okay, so yeah, so that was all. So I just want to conclude what I have discussed. So we have discussed about the necessity of Faddeev-Popov ghost in the non-abelian case theory. Then we have discussed the limitation of Faddeev-Popov way in the non-perturbative regime, and what is the way out by limiting the calculation within the first Gribov region. And we have also discussed some existing calculation for the deconfined phase, such as Gluon Thermodynamics, effective quark dispersion relation, second order quark number susceptibility, dielectron rate, etc. We have also discussed our recent result for the covariant kinetic theory and the transport coefficient for the Gribov plasma. Okay, so thank you for your attention, and that was all.